Graphs. Polynomial graphs have something in common. They don't all look the same. But right off the bat, we have a picture. Okay. That'll give you an idea of what they look like. They are curvy. Okay. Polynomial graphs don't have sharp points in them like absolute values do. And what else? We already looked at quadratic graphs, what's the shape of those called? Starts with a P.
Parabola.
Parabola, yes. So actually, guys, quadratics are polynomials. So a parabola is an example of a polynomial, but there are more than just parabolas. Okay, that's highest power of 2, right? Like x squared plus 3x plus 7 or something. Certainly the power can be 3 or 4 or 5 or 6 as long as it's a whole number. So what I'm going to do is I'm going to show you a slide of polynomial graphs. Then I'm going to show you a slide that aren't polynomials, and maybe you can from there deduce which is which. So the first slide is all polynomial graphs. All these 4 graphs are polynomials. Now they all look different, but they all have something in common. I just want you to think about what that might be. Right, good. So he's saying none of the graphs have something like this. That's a sharp point. That's a good observation. Anything else? What else do you not see?
No point.
All right, yeah, basically what she's saying is there aren't any graphs that are like separate points. That's true. No what? Okay, right. Yeah, good observation. So there are no endpoints. Okay, there's nothing like this, right? And there's no like line segments like this. So no endpoints. That's a good observation, which means that it's going to go to infinity or negative infinity on the left and right. All right, now these are not polynomials. So what she said is true. Certainly if it had an endpoint, it would not be a polynomial. What he said is true. This right here is called a cusp. More or less, it's a sharp point that meets a curvy point. So if you see that, you know it's not a polynomial. That indicates a fractional exponent, by the way, usually. This is something you guys didn't notice, but that's okay. What is the name of this right here?
Dotted line.
Dotted line called an asymptote. Okay. This would be an example of a rational function. Rational functions have asymptotes. And then this one's kind of hard to notice right now as far as why it's not a polynomial. But it has a repeating wave, okay? Kind of like you would see on a heart monitor or something, except those are not quite wavy, but they do repeat. But a repeating wave is an indication of a trig function. A trig function is not a polynomial. So here's what polynomials have. They can have curves and lines. However, they cannot have asymptotes, pointy edges, holes. That's something we didn't talk about, but notice none of these graphs have holes. Polynomials don't have holes. They don't have dead ends or endpoints. And the third and final thing is they do not have repeating waves. Okay, like we talked about before, you know, a graph like this is a repeating wave. That is not a polynomial. So the gist of this is if you want to identify a polynomial graph, the best way to think about it is look out for things it can't have. Okay? I mean, now notice it can be a straight line like that graph on the bottom left. That is a polynomial. That's like y equals x or y equals 2x or something. So if it's a straight line or it's a curvy line that goes to the left and right, it's going to be polynomial, as long as it doesn't have any of these things. But what we're actually looking for today is a lot of things that we looked at when we were looking at quadratic functions. So we're going to talk about domain and range. which is simple. And we're looking increasing and decreasing, relative min and max. A lot of this today is just review. So let's go ahead and look at the first example. So I can tell this is a polynomial. Like we said, the end behavior is what you were talking about. It goes down and up on the left and right, or it could go up, up, down, down, or whatever. But the point is there's no endpoints. Okay, it is a curve, which is allowed for polynomials. Have to go down here a little bit to see the bottom here. It doesn't repeat. It's not a repeating wave. There's no pointy edges. There's no holes. There's no asymptotes. So I know it's a polynomial. Now we're going to answer some questions about the polynomial. So asymptote is a good question where the graph does not exist. It's a dotted line. We're going to go more detail on that when we study rational functions. All right, so first of all, domain. Remember, to figure out the domain, you go from left to right and figure out what the possible x values are. Now, since this graph keeps going down and to the left, I know that beyond this, it's going to keep going. The domain's going to start at negative infinity. It's going to go all the way to infinity because this is going to keep going to the right, so I know it's going to cover all x values. So therefore, the domain for this one is going to be all real numbers over from negative infinity to infinity. Same thing for the range. If it goes down on the left and up on the right, it's going to cover all those y values, all the way from negative infinity all the way up to infinity. Increasing and decreasing, again, that's review. Increases, remember, when you talk about increasing, you're writing in terms of x. So it increases from negative infinity, this x value, up until negative 1. That graph will increase. Again, don't put 15. When you put increasing, you do it in terms of x. So it increases from negative 10 to negative 1. The y value goes up. Okay? And then it's going to increase from 3 to infinity, which means from this x value up until all x values to infinity, the graph will go up. Decreasing, it's going to decrease from negative 1 to 3. So from this x value down to this x value, the graph goes down. Has a relative minimum at 3, negative 3. Can anybody tell me what relative minimum means? The definition? Huh? Okay, it's lower than all the points to the left and right. It's not the absolute lowest point, right? Because there's points over here that are lower. But it's lower than the points around it. And then the relative max is a point that's higher than all the points around it. So the relative max would be negative 1, comma, looks like 15. So again, all this stuff is just review. Now, we are going to introduce a couple new terms here. Or one new term. I already mentioned it before. It's called end behavior. End behavior just means what happens to the graph on the left and right. So notice on the left it's going down, right? On the right it's going up. That's it. When you talk about end behavior, you just say what it's doing on the left and right. So since it goes down on the left, you put down for left end behavior. Since it goes up on the right, you put up. Up on the right. And then the other two things we need to mention are x and y intercepts. Notice it crosses the x-axis at these 3 points, negative 3, 0, 2, 0, and 4, 0. So those are our x-intercepts. Notice it crosses the y-axis at 0, 12. So that is the, that is the y-intercept. And that's it. So when you get the worksheet, you're going to have 4, 6, 10 things. You're going to have domain, range, increasing, decreasing, relative min, relative max, end behavior, x and y intercepts. That's it. All of this is review, actually. Let's look at one more example, and then I'll get you the worksheet. Actually, there are 2 more things I forgot. We didn't mention absolute min and max. This next graph will have either one of the 2. Let's see if we can make it smaller, fit it on one page. Okay. First of all, can somebody tell me what the domain of this graph is? Good. All real numbers because it goes up to the left and up to the right, so that graph is going to keep going up and to the left. So the domain is going to be all real numbers or negative infinity to infinity. Range, let's talk about why it's negative 10 to infinity. Well, the lowest point has a y value of negative 10, and the graph goes up forever, so that means the range is going to be negative 10 to infinity. Why is there a bracket around negative 10? Because it does touch at negative 10. In fact, it looks like it goes a little bit lower, but that's sometimes graphs look that way, but it doesn't actually go lower. All right, next, can somebody tell me where this graph is increasing? Okay, all right, it's going to be starting right here and increasing, right? That's actually about negative 2.5 or so. Okay, I don't mind if you're, whatever you put, it's a decimal, it's somewhere in between. It's going to increase up until this point, right? So I put negative 2, negative 0.6 for that one. Okay, negative 2.4 to negative 0.6, what I meant to say, because it goes somewhere about right there. I think on the worksheet there's no decimals. I just couldn't, for whatever reason, I use this one as decimals. Okay, then it goes down from negative 0.6 to, looks like about 0, looks like about 0.6 again. So it's going to decrease there. All right, and then going back to increasing, it's going to increase from 0.6 to about, looks like 2.2. So we'll go increasing 0.6 to 2.2. Remember, it's in parentheses, not brackets. And the final place in it increases from 4.3 to infinity. Again, you can put 4.2 or 4 point something, doesn't matter. Okay, and then decreases from negative infinity up until that same value. So we can just put negative 2.4. And we already talked about it decreases from negative 0.6 to 0.6. Finally, it decreases from about 2.2 down to about 4.3. So we can put decreasing there. All right, next up we have relative min. This one has 3 relative minimums. It has one here, it has one there, and it has one there. This first point looks like negative 2.3 comma negative 5.5, so that's what I put for that. Negative 2.3, negative 5.5. The next one is kind of hard to notice, but again, it's smaller than all the points around it. So I put 0.6 comma negative 0.2 for that. And then the final relative minimum would be down here, which looks like about 4.3 comma negative 10. So that's what I put for that. 3 relative minimums. And I don't know why minimum went away right there. That's weird. Was it there before? That's so weird. That just disappeared. Okay, whatever. All right, anyway. Anybody tell me how many relative max this graph has? How many relative maximum does it have? It has 2, yes. It has one right here and one right there, and that is correct. It does not have any absolute maximums because it goes up on both on the left and right. But relative maximum, I put negative 0.6, 0.4, and 2.2, comma 2. Does this graph have an absolute minimum? What is it? Where is it? There you go. A little bit past 4 and then negative 10. So for absolute minimum, just put positive 4.3 comma negative. There's no absolute maximum because it goes up on the left and right. So if the graph keeps going up on the left and right, there is no point that's the tallest, the highest. If it goes down on the left and right, then there can't be an absolute minimum. All right, end behavior, and then talk about x and y intercepts when we're done. Goes up on the left and up on the right. Now this one actually has 6 x-intercepts. 1, 2, 3. Here, I'm actually going to have to use my pen here. 1, 2, 3. Missed that one a little bit. 4, 5, 6.
Oh, so it's just everywhere where X touches.
Everywhere where it touches the x-axis. Yes. Now a graph can only have one y-intercept. In this case, it's 0, 0. It can't have more than one y-intercept, but can have multiple x-intercepts. And I will say this, I don't know really how big of a deal it is, but if it crosses the x-axis 6 times, that means the highest power has to be at least 6. Okay? So the more it crosses the x-axis, the higher the power is going to be, which is why a quadratic can only touch twice, because it has a power of 2. Now, it doesn't necessarily mean it's going to touch twice, but that's the maximum number of times it can touch. And that's it. Any questions about this? Pretty easy, right?